Welcome, everybody. It's my great pleasure and honor to welcome one of the founders of our field for the first time to Scotland and to Edinburgh. For those of you who happen to not know Charles Bennett, probably you don't do anything in computer science, because basically whatever you can imagine that is relevant to our field, in a sense, has been touched by Charles. When we wanted to write the first bio with for the advertisement on the lift, it was too long to fit the list and do the justice to about everything that Charles Bennett has done. You know, any concept regarding the link between physics and information from 70s when he got his PhD from Harvard has been blessed by Charles. So he has done a lot of topic on top of my head. Of course, the notion of reversibility, the link with thermodynamics, resolving the problem of Maxwell demon, invention of the quantum cryptography, BB84, the following the quantum teleportation. Anything funky about quantum, in a sense, has been done by Charles Bennett. And we will hear more about the recent stuff that he's excited about regarding the emergence of the classicality from the quantum complex systems. And without further ado, please, Charles.
Thank you. I'm delighted to be here in Edinburgh. Is this the right level of sound? Yes, okay, good. So this is going to be a pretty elementary talk, and those of you who know about quantum information, you can think of this as my ideas on how to explain it to the general public. Fortunately, the general public already understands information because of the information revolution. But like other parts of mathematics, this information originated as an abstraction from everyday life, as you can see even by the words that we use to talk about it. And this was a very useful abstraction, but whenever you make an abstraction, you keep some things and you throw away others. And it was, lately we've realized that in abstracting information in computation from physical experience, the founders of the field threw away a little bit too much physics. What I'm going to talk about is what happens when you bring back, in the most abstract way, the parts of physics that should have been included. And that's because they are, well, I'll say why they should be brought back. The problem is that conventionally, the information carriers that we think about in information technology are what a physicist would call classical systems. That is, that their states can be reliably distinguished, and to specify the joint state of two systems, it's necessary and sufficient to say the state of each part. But physicists and chemists have known this is not actually the way things in nature behave, especially small things like atoms, and that if you attempt to observe a particle state, in general you will disturb it, and only, even with ideal equipment, only getting partial information out about its state, and that's called the uncertainty principle. And then the other distinctive and maybe even more important feature of quantum physics is that two particles can exist in a state that is not properly describable by separately ascribing a state to each particle. And I hope to explain those things to those who don't understand them, and to help the other people become better explainers, because some of the great people in the history of quantum theory have said scary things like, if this doesn't make your head hurt, then you haven't been paying attention. I don't exactly know who said that, but Feynman and Bohr both said things like that. So what we need to do, though, is to cultivate an intuition for the quantum nature of information. That's what I'm going to talk about. So for most of the 20th century, the quantum effects were regarded as a nuisance because people had focused mostly on the uncertainty principle. So they thought, well, a quantum system is just a classical system that behaves unreliably, and we know how to deal with unreliability. It's an extra complication, but we can handle it with error-correcting codes and things like that. So let's develop the theory of computing and information processing on ideal equipment that doesn't make errors, and then we can add this extra stuff on afterward. But now it's known that the quantum effects have positive consequences of making possible new kinds of information processing. And I should say that this view of quantum effects as a nuisance is a view that I shared, and that my introduction to the idea that quantum effects could be a positive resource came through quantum cryptography, where you use a limitation of the adversary's ability to measure something as a positive, you take a positive advantage of it in order to guarantee your secrecy. So we kind of backed into it, and then understanding the positive effects that come from entanglement, now it's quite clear that quantum information is really a great and beautiful and useful generalization of classical information theory and computation theory. And will even allow us to understand some things we thought we understood about classical information. In particular, why quantum effects are pervasive and yet remained undiscovered until the 20th century. So despite these differences, there are important similarities which were not appreciated at first by quantum physicists and chemists because they thought quantum mechanics was a theory of physics and chemistry, not a theory of information. But if you put them in parallel forms, then we know that all classical information processing can be reduced to the processing of two distinguishable states, which we could call 0 and 1, and you only need a limited number of logic operations to do those processing. And then, given that, you can do anything that could be done with even more complicated logic operations. And the bits and these gates are independent of physical embodiment, which makes possible Moore's law. If I make a bit 1,000 times smaller and cheaper, it remains useful. Whereas if I make a car 1,000 times smaller and cheaper, it's not useful anymore. So similarly, quantum information can be thought of abstractly, not the state of a hydrogen atom or the state of a photon, but the state of a qubit. That is, a system that can exist in two reliably distinguishable states. And the processing, just as with classical, can be understood by operations that apply to one and two of these abstract quantum systems at a time. And similarly, they are fungible among different quantum systems. So the physical embodiment is you don't have to think about it when you think about, it's the hardware-software separation. You can make a theory of quantum algorithms that doesn't depend on knowing what information carriers you're going to be using. So, of course, classical information is our whole information revolution. Oh, it's too close to the microphone. That's what it is. Or the speakers. Where are the speakers anyway? Yeah. Yeah. Okay. So, maybe I should just stay away from these. Yeah. I need a. Let's see. Is this a laser pointer? No, it's a marker. very long stick. Anyway, oh, I can point with the cursor on the screen. How about that? Yeah, okay. Yeah, so anyway, all I'm saying is that what we think of as information processing, we should think of as classical information. Information technology only sticks out so far a little bit into the quantum realm. But this is a more general way of thinking about information in general, including all this. And it's a little bit like the way you can think about real numbers as a special subset of complex numbers, and complex numbers in a way the theory is simpler and more beautiful, and you can use them to solve problems about real numbers that are very hard to solve if you just think about real numbers. So by analogy, some things you might want to do with classical information or classical computation, if you have a quantum computer, you can do them easier. But I'm getting ahead of myself. So how do you explain quantum information to somebody who doesn't want to think about anything mathematically? Like if you say, if you're working in quantum, like you will always run into people who say, oh, what do you do for a living? And I do quantum information. Oh, what's that? Don't use any mathematics. This is what I say. I say, well, everybody knows what information is, which we call classical information. Now, if classical information is like the information in a book, quantum information is more like the information in a dream. And this means that if you try to describe your dream to somebody, eventually you'll forget the dream and only remember what you said about it. And it's very private. You can't prove to somebody what you dreamed, and you can lie about it without getting caught. So it's a little bit like that. But unlike dreams, there is a well-known mathematical laws that quantum information follows. Now I'm going to hurry through these things because you probably studied them all in Sunday school. Anyway, there's not very many of them. There's only about, well, here are the first four. So the point of it is, to every physical system there corresponds a space of dimensionality equal to the maximum number of reliably distinguishable states, and every direction in the states corresponds to a possible state of the system, and the spontaneous evolution is just a rigid rotation in the space. Then we got a couple more rules. And then this says, if you have a composite system, the Hilbert space is the tensor product of the Hilbert spaces of the parts, which I'm going to explain in better, less mathematical ways. And then this is the one, this stone tablets is suggested it's kind of religious subject because there are also different, factions or sects in the religion, and the one in purple is a group that believes that this fifth axiom is unnecessary. Well, anyway, so just as with religion, people express it in two complicated ways, and some people, I think even it was John Knox who lived here and in Geneva, and I went to his house the other day. He had an expression of the basic principles of, well, what he regarded as Protestantism, but I would say just religion in general, which he expressed in the Scottish dialect. And I was trying to get the picture of his expression of it, but basically it was, you love God with your whole heart and you love your neighbor as yourself. So anyway, there's a simple version of the principles of quantum mechanics, and that says that between any two reliably distinguishable states, there are intermediate states that are not reliably distinguishable in principle, and I'll give you some examples of this later. And then different states correspond to different directions, and any direction is a possible state, but states are only reliably distinguishable if the directions are perpendicular. Okay, so here's a good example of it, simple example of it. If I have a source of polarized light, you can think of the light being carried by particles, each of which has a direction associated with it that's perpendicular to the direction of propagation. It's called the polarization direction. So think of a series of these green photons coming along here. and they're all polarized horizontally. And if I send them through a crystal of some unsymmetrical material, such as calcite, calcium carbonate, they'll go through undisturbed. But if they're perpendicularly polarized, that is, polarized in the vertical direction, compared to the calcite crystal, they will get deviated and come out in a different way. And this means that you can use a polarized photon to carry one bit of information. However, the photon can be polarized at any other angle as well. Or since it's not the absolute angle of the polarization, it's the angle relative to the, so if this is the calcite crystal, the photon's coming along like this, it can be polarized this way, this way, this way, that way, any direction like that. And depending on the angle between the photon and the axis of the calcite crystal, it'll behave in this surprising way down here. If you send in some theta polarized photons, instead of what you might expect that would be deviated by an intermediate amount, some of them go into one beam and become horizontal, and the others go into the other beam and become vertical with probability cosine squared and sine squared of the angle. So we have a perfectly deterministic preparation of a system that even in principle will then behave randomly when you do this deterministic treatment of it. So that, you might say, is one of the central, I won't say a mystery of quantum mechanics, of the way in which it differs from classical mechanics and common sense. Now, as I said, it doesn't have to do with the absolute direction of the photons, but with their direction compared to the crystal. So what that means is that the vertical and horizontal photons can be distinguished by a crystal in this orientation, but if I tilt the crystal 45 degrees, then it becomes a perfect equipment for distinguishing the right diagonal from the left diagonal photons. But there's no way of distinguishing all four kinds. And that's not a limitation of the measuring apparatus, but a fundamental consequence of the uncertainty principle, or is what I said, that the polarized photons are characterized by a two-dimensional space of possible states, and only perpendicular directions are distinguishable. Any two perpendicular directions are distinguishable from each other, but no measurement will give a reliable outcome giving more than one bit of information about the state of a photon. So this was used, I think the first suggestion for using quantum effects to do something that's classically impossible is by Stephen Wiesner about 1970, but it didn't get published until 1983. And he invented quantum money, which here's a quantum banknote, and it has 20 polarized photons of those four different orientations, randomly chosen when the bank or the mint made the money. So in other respects, it looks just like ordinary money. And these photons live in perfectly reflective boxes, which is technically not feasible right now. Although there was just a few days ago some system where they stored the polarization reliably for about a couple of minutes. So anyway, so when this banknote is brought back to the bank knows which photon is in each box and therefore will make the correct measurement on it, try to observe it either with this orientation, calcite crystal, or with that orientation. If they all come out okay, it's good. But if a counterfeiter should try to replicate this money, they won't know what measurements to make. They'll get some bad results, and the chance of all 20 passing inspection at the bank is the 3/4 to the 20th power, which is a fairly small number. Anyway, a more practical application of the same idea is for where you don't use the photons to store information, but to transmit information. And we, Gilles Brassard and I, and our students built this apparatus and the software to run it. We successfully transmitted these polarized photons, actually dim flashes of green light, for a distance of 30 centimeters, and made the measurements at the receiving end in such a way that if somebody had attempted to eavesdrop them on here and send them on, we would have realized.
When was
We built it around 1989. The paper describing the result was published in 1992. Now it's practiced on a much larger scale through optical fibers over 100 kilometers, plans of putting them in space. You can see this apparatus was a piece of lab equipment built by theorists. But the principle of it is that measuring an unknown photon's polarization exactly is impossible. You can't get out the polarization angle by some sensitive equipment. You can't clone it. You can't duplicate the information, because if you did, then you would have a lot of photons and you could rotate the polarizing apparatus to get the maximum number of them. Essentially, that you would determine the polarization angle statistically. Now, a laser is a device that clones photons. So it would seem like a way of bypassing this limitation. But lasers work well only if the input signal is fairly strong. And in the limit of an input signal of a single photon, for fundamental reasons, the laser is just as likely to clone it, to produce two identical copies of it, as to not clone it and produce a random photon, which is called the process of spontaneous emission. And at the level of, at the one photon input level, these two processes have exactly equal probability. And if you do the math of it right, you'll find out that having two copies of an unknown polarization is half the time, and the rest of the time having the original photon and a random photon, that is no more helpful in finding out what the original polarization direction was. My colleague, Bill Wooders, who teaches undergraduates all the time, and he thinks a lot about how to teach this stuff. He says the way a quantum system behaves when you attempt to observe it is a lot like the way that the students were supposed to behave in the old-fashioned kind of British school, which I think is chiefly now practiced in other parts of the former British Empire rather than here. Anyway, the teacher is the boss, and the teacher will say to the pupil, "Are you vertical or horizontal?" And the pupil will say, "I'm polarized about a 55 degrees angle from the..." Teacher says, "I believe I asked you a question. Are you vertical or horizontal?" "Horizontal, sir." "Did you ever have any other polarization?" "No, sir, I was always horizontal." So keep that image in mind, because I'm going to try to explain how that actually fits in with a much smoother and more deterministic kind of evolution. But in order to make that connection, you have to think about entanglement, which I haven't told you about yet much. Well, I said that earlier on that there's a similarity between classical and quantum information, in the sense that you can break it down into elementary forms of data, just two distinguishable states, but now we have these qubits that can exist in superpositions. And just as you would make a diagram of an ordinary computer circuit with lines representing bits and gates representing logic operations on those bits, we can make a diagram of a quantum computer, which is the most general form of treatment that can be applied to a quantum system, in which the wires carry qubits and the gates are simple logic operations. I already referred to they're what's mathematically called unitary operations. I already referred to one, a rotation of a single qubit in its two-dimensional space is an example of a logic operation. But there are also two qubit operations, and this one is the one I'm going to talk about. You don't really actually need anything more than this one two-qubit operation. So what this is called, this is the, if any, I think we've got mostly computer scientists in here. You've probably run across the exclusive OR operation, otherwise known as addition modulo 2. Quantum computing people, being poorly educated in computer science and mathematics, invented another word for it called a controlled knot, but it's the same as exclusive OR. So the idea is that it flips its second input if the first input is 1, and otherwise it doesn't do it. So if I use a 1, this is the Dirac notation. It means this is a quantum state, but I'm labeling it by, I call it 1. And I use a 1 to represent a vertical photon and a 0 to represent a horizontal photon. So these are my two chosen orthogonal directions in that space. Then what this gate does is if the control qubit is a 1, the target qubit gets rotated 90 degrees. And if the control qubit is a 0, the target qubit is left alone. So being a quantum computer element, this has to obey the superposition principle. And that means if I give it a superposition of inputs, it has to give a superposition of outputs. And so let's give it a diagonal control photon. And that can be thought of as the direction that's intermediate between horizontal and vertical. And this normalizes it to unit length. And here we give it a horizontal photon for the controlled photon. Well, the result of this is the state that's intermediate in four-dimensional space between both photons being horizontal and both photons being vertical. And this is a state that doesn't have any representation as a state of the yellow photon and a state of the green photon. But it's a legitimate quantum state because two photons, I know that two photons, if one photon can exist in two reliably distinguishable states, two photons can exist in four reliably distinguishable states. Here they are, this, and that. And therefore, the space of possible states of two photons is four-dimensional. This is a direction in that space. And it's a direction that doesn't have a way of describing it as a state of one photon bias and the state of the other. So in more detail, this state, if you work out the algebra, is the same as that state, but it's not the same as a state like this, saying this photon is in this state and this photon is that state. So you can say the two photons are in a state of sameness, even though neither one has a polarization of its own. Now that makes sense that's words to talk about some pretty simple mathematics if you think in four dimensions. But if you don't like to think mathematically, what does it mean? They don't have a polarization of their own, but they're in a perfect state of sameness. Well, I did my graduate work amidst the distractions of the hippie era in San Francisco and Berkeley. In fact, some of my work was in Berkeley, California. And in those days, you could find a lot of people who were sure that they were perfectly in tune with each other, even though they had no opinion about anything. And I knew some of those people. Well, anyway, they also believed that if you have enough LSD, then everybody could be in perfect harmony with everybody else. So they were not very strong in mathematics. Now that if you understand entanglement, you understand a very important property of it is that it is monogamous. The more entangled the two systems are with each other, the less entangled they can be with anything else. So here's a pedagogic analogy of entanglement. I get this good idea from Bill Wooters, and then I kind of run it into the ground with my own versions of it. So we have two twin pupils, Remus and Romulus, and they're ignorant of every subject. I think they repeated the same year that they were in pretty much perpetually. But they're perfectly correlated. So if one teacher asks what's the color of grass when it's growing, he'll say pink. And then if the other one is asked the same question, also gives the same answer. But it's different. It could be orange another time, or even green. So what good is this entanglement? What can you use it for? Well, it can be used to do what would seem to be impossible because of the uncertainty principle. Suppose, and I'm going to represent this direction here as time and this as space. So what I want to do is I've got a photon, a green photon here, that's in some polarization state, but I don't know what state it's in. And I want to copy that polarization state exactly into another photon that has not actually ever touched this photon. So that would seem to be impossible because I would have to measure it, which would then get an approximate answer. And the best I could do would be to prepare the other photon as according to the result of the measurement. Well, quantum teleportation is a way of using entanglement to evade this seeming impossibility. But here's how, this is the best you can do, would be you measure it and then you send partial information and you prepare an approximate copy. It's not the same as that one. I'm not pointing here. It's not this, I can't point with my finger. Yeah, so this is at best an approximate copy. So here's how you use entanglement to avoid this problem. We start off with the original photon we want to replicate, and we start off with a pair of entangled particles. And we now do a measurement on one of the entangled particles and the photon. And this measurement completely disrupts the photons, but we are actually measuring the relation between them. We're not measuring each separate property of the photons. And we take the result of that measurement and send it over to the other entangled photon, which has never been anywhere near this one. And then we do a treatment, a corrective treatment to this one, and we get out exactly the same state as this one was in before we spoiled it. So here's a human analog of that, and thinking about not so much dreams, but suppose you've witnessed some complicated thing that's perhaps very scary and terroristic or something. Alice has witnessed this crime, and the FBI wants to interrogate her about it, but they don't want to trust it to the Boston police. So they invite her to Washington to be interviewed by a panel of experts. But she doesn't like to travel, and she refuses to go. And they were thinking of sending somebody, but they don't trust each other to interview her alone. Well, then one of the FBI guys volunteers, and he says, well, I don't know anything about this, so I'm less likely to influence her than any of you. Just ask my brother. And he agrees. So they send Remus to Boston. And they're instructed to have a kind of a speed date where they just decide whether they like each other. They don't talk about anything substantive. And it goes very badly. And Alice loses her memory of what she saw. All that she remembers is how much she dislikes Remus. And they tell her she can go home. And then they call Washington and say, well, looks like Remus and Alice don't get along. And then Washington say, good, okay, now we'll start asking questions from Romulus. And whenever he says yes, it means Alice would have said no. Okay, so well, anyway, the biggest reason that people are studying quantum information processing is the hope for a quantum computer. And the fact that because of this entanglement, you could have a greater scope for algorithms. And the most famous example of this is Shor's factoring algorithm. Now, even classical computers are getting faster and faster, so maybe this problem is now easy for a classical computer. You want it to take this number and find its prime factors. And, but at the time this was done, a few years ago, it took 8 months on hundreds of computers working at once. Now, by contrast, the reverse problem of multiplying these two numbers is fairly easy. You could do it without a computer if you had a quiet weekend. I've even started doing it myself. 3 times 7 is 21. That's where that 1 comes from over there. And then we carry the 2. So it's not really too hard to do without a computer. But of course we know that for classical computers, the best known factoring algorithms are, well, exponential is it's a sort of a stretched exponential. It's not quite as bad as exponential, but it's pretty bad. Multiplying two numbers is easy, factoring is hard. But for a quantum computer, both jobs would be easy. So that's a big impetus for trying to build a quantum computer. But that's not mostly what I'm going to be talking about. It's about the nature of classical and quantum information. And so I said that quantum information is a generalization of classical, which means that I have the obligation of explaining what classical information is. I have to tell you what a bit is and what a wire is and what a logic operation is. But it's really quite easy, and it has to do with cryptography. A classical bit is just a qubit with one of two arbitrarily but fixed orthogonal values. A classical wire is a quantum channel that conducts them faithfully but randomizes superpositions of them. Now, how does that happen? It happens, here's a classical wire. And what's really going on in a classical wire is that it's interacting with some element of the environment by means of this XOR operation. So if the data is 0 or 1, the environment gets a copy of it. But if it's anything else, it becomes entangled with it. And then if this is thrown away, this thing behaves randomly. So a classical channel is a quantum channel with an eavesdropper, and a classical computer is a quantum computer with eavesdroppers listening to all its wires, which is harmful for privacy. Yeah, that's obvious. But for some computations, like factoring, it's actually also harmful for the efficiency of the computation. It's not obvious, but it's true. Okay, so now I'm going to talk about the origin of randomness and the ambiguity of the past. Like, I'm not going to talk about quantum computers anymore. I'm going to talk about why this quantum way of looking at things and thinking of things in terms of entanglement will help us understand the world that we live in a more unified way, including things like why is it that things in the past and things in the future, we are limited in our ability to predict them or remember them. Well, this idea is an old idea from, I think, even before the 19th century, basically growing out of the work of Newton. And it was expressed by Laplace, who said that if you had a perfect knowledge of the present state of the universe, or you would be able to predict its entire future and its entire past. There would be nothing hidden from you. And the limitations of our human knowledge just come from insufficient computing power or insufficient knowledge of the initial conditions. Now, quantumly, I would say the way most people understand quantum theory in terms of the uncertainty principle, the future is less determined. Even an omniscient God wouldn't be able to predict whether a particular atom, radioactive atom will decay within its lifetime, or how a diagonally polarized photon will behave when it meets a calcite crystal. And then there's this asymmetry. We remember the past much better than we can predict the future. And this actually can be quantified if we go to Google Books and look for the phrase 1970 or any other phrase and see how often it appears as a function of the year of publication of the book. And it goes like that. So the phrase 1970 was measured, this is the absolute frequency. People never talked about it very much. 0.02%. That's pretty much the fraction of potassium atoms in your body that are radioactive due to potassium-40, which has like 1.5 billion year lifetime. Much of the radioactivity in your body comes from potassium that's there naturally. Anyway, it's not as harmful amount of radioactivity anyway. But if you're really worried about it, you could ask for depleted potassium from sources like Brookhaven Laboratories. And it costs about $1,000 a milligram, I think. So anyway, getting back to the, anyway, that wasn't originally intended to be part of my talk. So these things, there's an asymmetry, and we talk a lot about things that have happened in the past, but we don't talk about the things that are about to happen until they've happened. Now, unlike the future, the past we consider that it's things have happened and they've really happened or they haven't happened. But of course, if we know quantum mechanics, we know there's some things that you might say happened in the past that are a little ambiguous as to whether they happened or not. And a good example is this is given by the equipment known as an interferometer. And this is you can build it, you can actually build it with calcite crystals, but this is a version that's built with half-silvered mirrors that have a 50% chance of letting through a photon and a 50% chance of reflecting it. We also put some ordinary mirrors and then another half-silvered mirror. And if all these 4 optical path lengths are equal to within a wavelength of light, which you do by putting it on a pretty rigid table in a room free of vibrations and wind, then if you send a photon in here, it follows both of those paths, but it always comes out here. And that's a little strange behavior because you would say, well, it might have gone down and it might have gone up, and then whichever side of this mirror, if it comes at it from this side, it should have half a chance of going down and half a chance of going right. Similarly from here, but in fact, it always comes out there. Now, if you block the path by sticking your finger in the way, then what happens, of course, half the photons hit your finger, and the other half reflect off this mirror and then go half into this beam and half into that beam. So by putting your finger in the way, you've increased the amount of photons that come out one of the X's. And so this is something that is easily understood if you think in a quantum way. You say that the photon followed a superposition of these 2 paths, and then the superposition was converted back into a single path. It's a reasonable, it's a completely unitary transformation of states in the quantum way of looking at things. Here you might say the system has a 2-dimensional Hilbert space of which polarization the photon is in. Forget about it. The polarization is not, strike that from the record. We'll see another version of that. But anyway, the point of it, when you have a superposition like this, it was actually wrong to think about the photon being here or here. And so you say the past event of whether it was here or here is really something that never did properly have an answer. And so you might say that, speaking in a religious way, even God doesn't remember which path it followed, but that's a little bit blasphemous because, as Danny Greenberger said, any God who would want to know which path it followed, he wouldn't believe in that God. So this looks very different. So we have this evanescent information which path it followed, and now we have this brutal irreversibility of how something behaves when we measured it. How do we harmonize those views? Well, we go back to the hippies, and it's true that most systems in nature are, other than little ones like really small ones like photons, interact with their environment. Their environment eavesdrops on them and becomes massively entangled. And this destroys any entanglement between internal parts of the system and degrades it into mere classical correlated randomness. So the parts of the system are no longer, once the environment wanders away, are no longer entangled with each other. Well, let's look at this. This is what is termed the monogamy of entanglement. A and B are perfectly entangled. Here's how we make them entangled. I showed you that circuit. And now we say, well, let's try to make more copies of this, share this amongst a larger group. So we bring in another photon in the 0 state, and we do the same thing before. We try to make a third copy of it. And instead of having 3 photons that are all in the same state of total ignorance except being totally the same, we get only classical correlation here. The 2 photons are the same if you measure them along one axis, but if you measure them along another axis, they'll only be partly correlated. And so this can be captured in the sort of social saying that 2 is a couple and 3 is a crowd. So let's look back at this experiment with the polarized photons. And let's say we don't measure them actually. We just let them go into the 2 separate beams, and then we do something. We don't look at them. And I'm saying this behavior, which shouldn't even be thought of as behavior, can be undone. And what we do is we put them through a piece of actually a thin slice of calcite will do, that converts horizontal photons to vertical and vertical to horizontal. And then we aim them back into a calcite crystal, and what has happened here gets undone. And not only do they come out in one beam, but they come out with exactly this polarization that they seem to have forgotten before. So in terms of Wooder's analogy, it's the public embarrassment of the pupil in front of the whole class that makes him forget his original polarization. So this gives us a clue into what it means, where does classical information come from, if everything really is quantum information to begin with. And this is a way of looking at it. This is the general field of this is called decoherence theory. This is a particular brand of decoherence theory that was popularized by Wojciech Zurek and Robin Bloom-Cahoot and my postdoc, Jess Riedel. And they, well, I think it's Zurek is the senior member of the team, and he's to blame for this name for it. He calls it quantum Darwinism. But I think a better name would be quantum spam. And the idea is that if we have a quantum system and it is observed, here's the quantum system, repeatedly observed by different environments that don't interact with each other after they've observed it, then along some axes, each of the environments gets a copy of the information in the system. But along other axes, the system is only correlated with the whole of the environment, not with any part of the environment. So it says, the reason he was calling it quantum Darwinism is that some information about the system gets massively replicated, and some information gets hidden in complex correlations that are nearly unobservable. Well, anyway, speaking of privacy, there seems to be not a lot of it around these days. We've got a lot of easy-to-use cameras and cheap data storage. And this can be very, very dangerous in the hands of despotic rulers. But it sometimes be good, also deterring individual misconduct as well as governmental conduct. So in many situations, the bad guys want privacy for the misdeeds, and the good guys want publicity. So it's actually not very common in New York or Massachusetts, but a good many Americans thinks that it's healthy for society if everyone could carry a gun. But I think it'd be better for everybody to carry a camera. So there's a nickname I have for this. It's the Second Amendment for the Fourth Estate. The Second Amendment is part of the Constitution, U.S. Constitution. It says that everybody has the right to carry a gun, subject to some limitations, which in practice there's very little limitation. The Fourth Estate is the word used to describe the journalistic profession, which now includes probably amateurs and bloggers. So a Second Amendment for the Fourth Estate should be that every shipman should be able to carry a camera and record what they see happening in public. And there would be some limitations. You can't use it for blackmail. And this is not an old idea. Just maybe 8 years ago, I saw a billboard in Delhi that says, if you see it, shoot it. Every citizen a photojournalist. Well, now, for some reason, CNN doesn't use that billboard in the United States. But in fact, things are developing in a good direction because cameras are proliferating much faster than guns. How many people here in this audience have a gun with them at the moment? How many people have a camera? Okay, so I think we're winning here. Okay, so it seems like there's several levels of privacy. We've got the quantum level, which maybe you shouldn't even think that the information ever existed. And then there's the classically private level. The information has been replicated and stored in a lot of systems, but not widely enough distributed for it to be easily found by humans. And then, of course, the kind of information that politicians lie about. So this modern world looks rather different from the ancient world, where there was a lot of information that was public at one time, but then was lost. This sort of pre-Gutenberg era where literary works were never copied in extremely large numbers, and sometimes all of the copies were lost. Good example is the poet Sappho, who was extremely famous, but some like less than 5% of her work survives. It's just a handful of poems. And this happens in all cultures, and sometimes in a very sinister way. The emperor who unified China in the 3rd century BC wanted to suppress knowledge that might be destabilizing the country, and required that all books be burned, and with severe penalties for people who didn't do it. And so fortunately, some of the scholars memorized most of the important books, and then, since he didn't last very long in office, reconstructed them afterwards. And Sappho's poems were mostly lost just through not sufficient number of copies and her dialect of Greek having fallen out of use. And then here's another really poignant example. Apparently this philosophy, in a way it's like what happened to Sappho. Much of what we know about her is what other people said about her, rather than the original work. This is a philosophy, these were maybe the first atheists. And they also didn't believe in reincarnation. And so the Hindus and Buddhists didn't like them very much and criticized them, but all their original documents are lost, and we only know what their opponents said about them. Well, I would say that even in today's world, a lot of macroscopic information is going to get lost, or it might get lost. It may get lost in practice, because nobody cares enough about it to record it. And this is sort of a counterexample, because I thought these were interesting pattern of cracks and raindrop craters in a riverbed in Las Vegas, USA in 1965, so I took a picture of them. But they didn't last very long in nature. They were washed away a few days later. And so the question is, if nobody had photographed them, would a physical record of them still exist? It's a philosophical question. Would a physical record of them exist in the universe or not? And I started off wanting to believe that this was true. I mean, if you burn a book, then you ought to be able, in principle, to recover the state of the book from the smoke and the ashes. But of course, you should consider also the heat, the photons that come out. I guess the reason for my prejudice is that I was irritated by what they call the postmodernist philosophy a few years ago, which alleged that the past, or maybe even the present, doesn't have an objective reality independent of human belief systems. And I thought that was very arrogantly anthropocentric. Science shouldn't put people in such an exalted position. But anyway, I later changed my mind. I think some information is lost not from the universe, but from the world, because there's so much information flowing into the world and out of it compared to the world's information storage capacity, large as it is. So we can estimate this as the heat coming into the Earth is about 300 watts per square meter, and about the same amount leaves, and you can work that out to be 10 to the 30th bits per square meter per year. And then suppose you wanted to save all this, and what's the biggest tape recorder in the world? It's the formation of new rock at the mid-ocean ridges, where atoms are frozen into position. And if you had control of all that, how much information could you store? Well, it was about 8 orders of magnitude too small to remember everything that had happened on the Earth. So maybe a lot of information is lost. And if this goes away in the form of thermal radiation into the sky, you are not very likely to be able to catch up with it, because it's leaving at the speed of light. So we have a new level of the hierarchy of information, escaped classical information. Now, let's try to understand some of the characteristic mysteries. Now, here's some information that's pretty clearly classical, but we're not able to access it. Apparently, for several centuries, they used to drop a gold wedding ring into the water in Venice. to symbolize Venice's marriage to the sea. Now this gold is pretty stable and is probably down there in the mud somewhere, but nobody knows how to find it. Then there's this lost literature, and then information that nobody cares about, and probably, although it's hard to say which of it is gone, most of it's gone. Like, where were the raindrops the last time it rained here? Nobody cares in most cases. And well, I didn't eat actually any rice today's lunch, but I made this slide when I did eat rice. Now, of course, some of this information might get back to the Earth. Suppose we have some old TV broadcast that we forgot, and somebody on one of Jupiter's satellites, recorded it and sent it back to the Earth. So you could call that an extraterrestrial fossil. But if you tried to capture all of the thermal radiation that escaped from the Earth, you would have a serious climate change problem. So let's try to understand this in terms of this picture which identifies the randomness as coming from having a perfectly deterministic unitary evolution, perfectly smooth evolution of the quantum system, but then losing track of part of it, losing it in eavesdropping paradigm. So here we'll say we have some raindrop that falls in one place or another, and then it gets washed away. Its former physical location doesn't have any stable earthly embodiment. Of course, there are lots of replicas of where it went that are going off into space, but we can't catch up with them. So let's try to describe this in terms of quantum state evolution. So we have the thing being a deterministic quantum process. It actually falls in a superposition of places, and the brown letters represent the terrestrial degrees of freedom, and the blue ones represent the celestial ones, the ones that are photons going off into space. And we would say, anybody in the world would say the drop fell in one place. But God would say, well, actually, I'm seeing the thing from a more Olympian way, and I see both outcomes happening. But I know all the people on the Earth agree that one of them happened, and they agree which one it is. And then after a while, there's less terrestrial storage of the information and more celestial storage. And then finally, there's nothing left on the Earth about it at all. So the Earth is in a single state, and the sky is in a superposition of states that we can't observe because it's all in photons that are too far away for us to catch up with them. So the conclusion of this is that the escape of the last replica from the Earth restores our terrestrial observers to a more detached and Olympian viewpoint in which both outcomes are equally real. So this escaped information is not so different, after all, from which path the particle followed. And this is part of the popular culture. You might say that you can buy a plaque that says, you can put it on a tree or something and say, in 1832, nothing happened here. Now, of course, in 1832, things did happen, but maybe almost everything that happened in 1832 was not recorded, and in a physical sense, it is all escaped information where in order to find out about it, you'd have to leave the Earth at faster than the speed of light. Well, now let's see. I had a third part of my talk, but I think this is maybe a good place to declare an end and hop to the very, very last end of it. Because I think I've taken most of the time, but I didn't want to go slower. So here's the conclusion. Quantum mechanics gives us a world where many aspects of the future are inherently ambiguous. And it's not because there's something we don't know, it's because there's something that's unreasonable to ask. Monogamy of entanglement gives us our classical world, which in a way is an illusion. But we depend on it for everything that we see. The fact that there's information that I'm looking at this letter E, and we all agree on it. That would not be true in a quantum world. The fact that there are multiple copies of information that are in agreement with each other doesn't happen naturally in quantum mechanics. It happens as a consequence of special conditions, that is, the conditions that we exist in. The world is out of thermal equilibrium, but it's being observed all the time by us and by these photons going out into space, which means that everybody here thinks that something happened, and they all agree on what it was. Now, this is really largely a philosophical distinction, and when I gave this talk to one of my fellow scientists who has a more of a Bayesian approach to things, he said, I would rather believe that Sappho's lost poems exist than that the quantum state of the universe exists. But it's really just a philosophical question. And I say the Earth retains a lot of information about its past, but a much larger amount escapes into space, making many aspects of the Earth's path nearly as ambiguous as its future. And a thermodynamic question, which I didn't get time to talk about, is the thing that not only, it's been well known that you need a system to be out of equilibrium in order to get complex behavior. You know, we all need to eat food. If we just put ourselves in a box without any food, we would come to thermal equilibrium and we would die. Before that, actually. But it also enables classicality, and that's the new insight that comes from decoherence theory. All right, well, thank you for your attendance or attention. Well, I think it's, I've looked around and there's been a fair amount of attention as well as attendance.
Perhaps we have time for some quick question before we go to the reception and have longer discussion.
Well, it's a kind of a fuzzy question, so that's probably appropriate. When people talk about maybe having memories for life, where you can maybe record everything that possibly has happened to a person. With this kind of loss of memory, I'm kind of wondering, will people fade away? Also, every time you interact with it, will you effectively, by interacting with this entangled state, you would disequilibrialize it and effectively cause this memory to fade away, or randomize?
That maybe sounds like a fuzzy question to you, but it touches on a lot of things. The information loss I was talking about was really the loss of classical information. The information that was at one time entirely distinguishable, but the carriers of it escaped from the Earth. So, but when you speak about memory scans, that gets into the question of whether quantum behavior, or quantum entanglement is an important part of consciousness. And the consensus among of quantum information theorists is that it is not. That the human head is such a hot place that is so embedded in eavesdropping activity, being able to listen to your brain waves is just the least of it, that quantum interference plays very little part in consciousness, maybe none. The main person who doesn't think this is Roger Penrose, and I think he's got a reason for thinking that. It comes from identifying two things that we don't understand, quantum gravity and consciousness, and thinking that they might be the same thing. But most people who've studied this don't think that way. So the question is, if you wanted to store the information in your head enough to create a replica that would have the same thoughts, you probably could store it in a medium that was not much larger than your head. It would be a problem to do it for everybody, but maybe for a rich person and could do it, because we do have extremely compact information storage media. For example, consider carbon monoxide. If you cool it low enough, it performs as solid, and the molecule is nearly symmetrical, but everyone can carry a bit depending on which way it's put in. And the problem isn't the stability of it, its the problem is writing it and reading it. But to store the complete information sufficient to reproduce a person's state in a form that they would be thinking the same thoughts, they would be alive, probably is only technologically impossible, but not impossible in principle.
So you gave us illustrations of how susceptible superposition was to environmental factors. So are we ever going to be able to preserve superposition in a sufficiently large number of qubits that we will get a quantum computer of the kind that is anticipated?
Well, that was the progress in quantum information and quantum computing since 1995 was based on that challenge. It was said, we came out, Shor's algorithm was 1993, I think, 1992. And people said, well, you know, that's interesting in theoretical computer science, but it's like thinking about NP. It's something that you can never build a thing that does that. But then there was the great growth of quantum error correcting codes and discoveries of more and more ways of stabilizing quantum information against this environmental eavesdropping. And the consensus now is that it's difficult but possible, and is only engineering barriers that stand in the way. Not everybody believes that. Some people believe that it's going to be impossible in principle. But the theory of quantum fault-tolerant computation is like a doubly hard version of the theory of classical fault-tolerant computation. And you might say the reason is that in classical fault-tolerant computation, you don't want information leaking into your computer from outside and changing the data inside it, but you don't care if it leaks out. In quantum fault-tolerant computation, the nature of quantum information is that there is always bidirectional leakage. There's either no leakage or there's leaks in both directions. And you have to prevent it, and it's about twice as hard. And as I say, there's steady progress. There's operations on 2 and 3 qubits that get very 99% fidelity. There's this information storage for many seconds in a single qubit. So it looks like it's going to be a hard slog, but eventually there doesn't seem to be any. I often compare it to fusion power. Everybody knows it's possible, but it may not happen in our lifetime.
It's always 30 years away.
Yeah.
Any other questions? In that case, just remember that there is a reception outside. Let's thank our.
This production is brought to you by the University of Edinburgh.